Hello guys. Alright, I'm just gonna do the register quickly. Who else we got? So Sam, Joseph, and Frank. Cool, still missing a few people. We will get started in a sec. Alright, yeah, okay. Um, Good. So today we're going to be looking at hypothesis testing, and this lecture needs to go quite well because yesterday, the first time I taught this, the iPad broke. Second time I taught this, I had hiccups. So yeah, I'd like to get one good take of this lecture. And then I need to speak to you guys at the end as well about assignments and skills checks because we're going to do those. Hello, Casper. Okay. So hypothesis testing. We did a bit of this last year. We did the binomial last year. This week and today we're going to be looking at normal, and then after Easter we're going to be looking at correlation and how to hypothesis test correlation. Okay, so and they all have things in common. They're not completely separate types of maths. They do similar kind of things. So binomial hypothesis test. Hopefully you guys remember from last year is a test to see tests to see if a probability is accurate. So the idea is somebody makes a claim about a probability. So I don't know, a gambling company says the chances of winning is 0.7. So it's a claim chucked out there. And that claim refers to a population. So the population is everybody playing the game. The probability of winning the game for each person for the whole population is 0.7. What we do for one of these tests is we take a sample. So we take a smaller group, which is the number of trials. We take a smaller group from that population. We see how many wins we get, and we say, okay, we won this many times in our sample. Does that seem likely if the population was stated to have a probability of winning of this? So with all these things, we're taking a sample, doing something with the sample, in this case, finding how many wins we get, and seeing if it's likely based on what the overall probability was meant to be. So I'll give some examples of these as well. So for the first one, I've said chances of winning are 0.7. Okay, so that brings us to the normal hypothesis test. So for the normal, we're not going to be checking probability because obviously probability is one of our what's the word I'm looking for? One of our, not variables, one of our, it'll come back to me later. No, it's gone. N and P in binomial. We use mu and sigma in the normal distribution. So in the normal distribution, again, we're going to have a population. And for that population, we have a stated mean. So they might say the mean of this is something. We're then going to take a sample from the population, see what our mean is, and say, okay, does this mean seem likely for our sample given the mean of the population is meant to be whatever. So this one tests parameter, that's the word I was looking for. So binomial tests the probability parameter, normal test the mean parameter. So tests if mean of a sample represents the mean of the population. So like I said, the mean is stated as this. Is that likely to be true given that we found the mean to be this in our sample from the population? So that's what we're kind of looking at. Cool. So for an example you might have with this one, and we'll look at a question on this in a minute, is e.g. the phone battery lasts 12 hours. So when you buy a phone, they might tell you, the battery life is 11 hours, 12 hours. That is come from a mean. So they've gone, okay, here's my phone. What's the mean of it? Cool, 12 hours, good. We could test that. We could take a sample. We could get some phones. We could work out the mean battery life and say, okay, our mean's different to your mean. Is that likely given the distribution we're dealing with? So that's what we're going to be looking at today and Friday tomorrow as well. And the last one I'll talk about briefly, because we are going to spend some time on this after Easter, is correlation. So we can test the correlation, do a hypothesis test on it. So it tests if the correlation of a sample let's make this clearer. If the correlation coefficient which is R, we call it the PMCC, for a sample represents the correlation coefficient for the population. So one more time, in each of these tests we are looking at a population with either a probability, a mean, or a correlation coefficient, and we're taking a sample and we're saying, okay, we found this, we found this, we found this. Is that likely to be from this population given those initial parameters? So that's what we're doing with hypothesis testing whether your sample is likely to have come from a population. In other words, is that population lying? Is it true? Is it accurate about the parameter that they told you? Okay, so we're going to try one of these using iPhone battery life. So I did a Google and I found that the most expensive, best iPhone apparently is the iPhone 11 Pro. And it claims to have 11 hours of video playback. Cool. So that's a mean, obviously, stated for our battery length. So for my population, we'll use B for battery. The battery life is a normal distribution with a mean of 11 hours. And I had to make up a standard deviation. I reckon 1.5 hours standard deviation seems about fair. I'll let them have that 1.5 deviation from that mean. And just remember that x is mu and mu and sigma squared. Cool. All right. So let's say we now go take a sample. So sample. So now I'm a YouTuber. I have some big dollars. I'm gonna go out and splash some cash on a set of iPhone 11 Pros. I'm gonna buy 10. So if I buy 10 iPhones, and I'm gonna get all the other maths YouTube sensations to buy 10 as well. So Exam Solutions buys 10. And Dr. Frost, he buys 10. Physics and Maths Tutor, he buys 10 as well. So we've all bought 10 phones. And we're all going to take the average of our 10 phones' battery lives for streaming video. So we all find the mean battery life for our samples. Okay, so we've each found the mean battery life for our sample. That's right, Sid. Just rewatch the video. Maybe if you rewind and start it earlier, that'd be good. Just while I'm here, some of you missed Monday's lecture. So I think Sam, Will, Sid, Zach, Lottie, and then Joseph and Sam, you guys might have not watched all of it. So if you could make sure you go back and watch the rest of last lecture, that'd be good. All right, so yeah, we've the four of us maths big deals have got our samples of 10 iPhones, and we've all found the mean battery life for our samples. Those mean battery lives should also be normally distributed because they came from a normal distribution. If you take a sample, each of the samples you take, if you average those means, they should be normally distributed as well. So we can say the sample means, let's use B with a bar on it. So the sample means are also normally distributed with a normal distribution. Thanks, Joseph. They are the best band on the planet. Normally distributed with a mean. The mean needs to be the same because it's from the same population, so we still get mu. And then we get sigma squared. Now, the standard deviation is going to be different. Standard deviation up there was sigma. We've only got 4 bits of data, so it's not fair to use the same spread because obviously we've got 4 data. It's not going to have the same spread. So how we work out the spread for our sample mean distribution is we use sigma squared over n. So we need to divide it by how many sample or how many bits of data we've got in our sample. And that will give us a distribution for the sample means. Okay, why we've done that is we can now use this as a test to see if the mean they've given us fits this distribution. And if it doesn't, we can then claim that they're lying and they'll fail the hypothesis test. So we're going to try this as a question on the next slide. So if I scroll over. So we said battery life was N11 1.5 squared. How come it's not fair to use sigma? Okay, remember sigma, Dan, is the spread of your data. Spread of the data. If we've only got 4 bits of data, it's not going to have the same spread. So we can't use the same spread. We have to basically squash our spread, because it's an average, by n. So we divide our variance by n to get a more realistic spread for our 4 bits of data. Because otherwise, if we tested it with the whole set of data, it's just always going to come out the same as what they've said. So we make it smaller, so we kind of fit the distribution to our sample, so we can have an expected variance within our sample, so we can then make some comparisons. Otherwise, it wouldn't make any sense. We'd just be comparing the same distribution with the same distribution. For an example, if Apple make this claim, they ought to have made that claim on a big sample, 1,000 iPhones. If we find that the battery life is vastly different with just 10 iPhones, that obviously is more statistically interesting than if we found the spread was different with 1 iPhone. So you have to account for the number in your sample. If we went back to Apple, if we did one phone, say, hey, my phone lasts for 10 hours, they'll be like, for whatever. If we did a sample of 10,000, you've got a lawsuit. So it's you got to account for how many are in your sample. Okay, anyway, so our battery life for the population stated as this. We've used our mean battery life, so our sample means as this one, mu sigma squared over n. So I'm going to put all the bits in there that we know. So my mean battery life has mu still 11, and sigma is going to be 1.5, or variance is going to be 1.5 squared over, what was my sample? 10. Cool, so I buy 10 phones. I can't spell today. At least I'm spotting it. I buy 10 phones, my mean battery life is 10 hours. So the question we're saying is we're going to do test at the 5% level if I can complain. All right, so we need to state some hypotheses because we always do. So null hypothesis, same as back in binomial. Null hypothesis assumes that nothing has changed. So we're going to assume that the mean is still 11. The alternate hypothesis, I believe that the battery life is less. So we're going to go null hypothesis or alternate hypothesis mu is less than 11. So there's my hypotheses. We're looking at a one-tailed test because I'm only doing less than. All right, now the idea is if we plot our sample mean distribution with our mean of 11, so this is our sample mean distribution, we're trying to see how likely is it that my battery life was 10 hours. So we're trying to find this probability. If that probability is less than 5, it means that it's less than 5% likely that a battery life was 10 hours based on this distribution. So based on Apple's claims, our sample of 10, I shouldn't find a mean of 10 hours if they're telling the truth. So think that through again. Their distribution says it should have 11 hours. There's some standard deviation because it's obviously every single phone won't be the same. 11 hours. So we've said there should be a standard deviation of about 1.5. That would be fair. If out of my 10 phones, my mean is 10 hours. Now think about that. That's a lot less. On 10 phones, if they claim it's 11, 10 phones, we're trying to find that probability. If that probability is less likely than 5%, that's quite extreme. It's saying this really shouldn't have a mean of 10 when you only did 10 phones to test it. So we're going to find this probability, see how likely it is. If it's unlikely, if it's less likely than 5%, they're going to fail the hypothesis test and we'll assume H1. That's the gist of what we're doing. So I'm going to bring up the old calculator. And oh, that looks horrible, doesn't it? Let's fix this. So I cut the bottom off it because I was fed up of it taking up all that room. So hopefully you guys can see that. I'll put myself up above it. Here we go. So, cool. All right, so we're going to go to statistics. Oh dear, I've got no room here. So go to statistics, go to distribution, and we're looking normal distribution. We're doing an NCD because I know the values I want to find the probability. My lower value, we put in 0. Upper value, 10. Sigma, this is important. Pay attention to this. What's here in this table, here, this is the variance. I need to write in the standard deviation in my calculator. So variance, standard deviation. What do? I need to square root all this stuff. So square at the top, 1.5 squared is just going to be 1.5. So type that in, 1.5 divided by 10 is part of the variance, so I need to put root 10. It's really easy to get that wrong. So we're going to type in the square root of 10. Cool. Put in mu is 11, and we're trying to find what this probability is. So we can go down, we can do a sketch. Looks pretty unlikely. So what do we get? Probability equals 0.118. 0.018. What does that mean? Well, if we get rid of the calculator, All right, so we're testing at 5% level. Is that more or less than 5%? That's 1.8%. Ooh dear, 1.8%, which is less than 5%. Therefore, this is critical. So it means it's very unlikely. In fact, there's only 1.8% chance of my mean being 10 if the mean is actually meant to be 11 based on my sample size. So it's critical. So therefore, I've run out of space here. I'm going to get rid of some stuff. Therefore, reject H0, accept H1. There is evidence to suggest the mean of the population is less than 11. So I can complain, basically, is the point there. Cool. All right. Can you guys just have a think about that? Ask me if you got any questions. This is a basic one. The ones we normally do won't be like this because this is all done with probability. We're going to be finding critical regions for when we do it because it's a bit safer and it's better to find critical regions. So have a read through though. All right. Assume that you guys are all okay with that. So let's move on. Right. So we're going to try this question. Just move this up a little. Cool. So we have a machine producing bolts of diameter d. Cool. And d has a normal distribution. Okay. Why does it have a normal distribution? Because it's a machine producing something. It doesn't produce the same results. Every time there'll be a tiny bit of deviation. So the normal distribution has a mean of 0.580 and a standard deviation of 0.015. So let's write that down. So we got bolts d, which are normally distributed with a mean of 0.58 and a standard deviation of 0.015, which we need to write squared as well. Cool. Okay, the machine is serviced. Okay. After the service, a random sample of 50 bolts is taken to see if the mean has changed. So that's kind of important. You've serviced your bolt making machine. You're worried that you might have put it back together wrong or adjusted something wrongly. So let's make 50 bolts, find the mean diameter, see if it's changed. Because if it's changed, we're no longer making bolts very well. So, okay, so we take 50, we're trying to see if it's changed. The distribution is still normal with the same standard deviation. So we're going to do a critical region test at 1%. Okay, cool. So my sample means should also be normally distributed. It's with the same mean, 0.58, and a standard deviation of 0.015, square it for the variance, over, what was my number of samples? 50. So there we go. Okay, and it says this time we're trying to see if the mean has changed. So they don't know if the bolts are wider or thinner, they're just saying it's changed. So we've got a two-tailed test. So we need to do our hypotheses, H0 mu equals 0.58 and H1 mu is not equal to 0.58. So it's a two-tailed test. Okay, so I need to, well, I don't need to, but I'm going to sketch it. Quick sketch. So the mean should be 0.58. And we are looking for these critical values. It's asked me to test at the 1% level. So same as in binomial, we need to split that percentage up between each tail. So we're going to have 0.5% for each tail. All right, let's write this as a decimal. So we've got 0.005 for our percentage. So that's the 0.5% level. And same for the other one as well, 0.005, which can go in there.
Cool. Okay, so we're trying to find what those values are for our critical regions. We want to find what this value is, and we want to try and find what that value is. Okay, so if we go to our calculator, we're going to plot the sample mean distribution, we're going to put in the probabilities, and we're going to try and find out what our values are. So if we bring back the calculator, and this one's going to be inverse normal because we know the areas and we want to find the values. So inverse normal, inver. Tails, we're going to have to do both. So let's start with the left-hand tail. Remember, if you're doing this on the class whiz, you need to be a bit careful about which way around you do things. So we need 0.005. So 0.005. The sigma value there, we're going to type it in. So 0.015 divided by square root of 50. Don't forget to square root it. So square root of 50. And the mean is 0.58. 0.58. Cool. Right. So let's execute it, and we found our left-hand value. So 0.545. No, 0.5745. So that's this value here. Going to do the same thing now for the other region. So we're going to do tail to the right. Because the probability is the same, I can just change my tail to the right. Nice. Push equals, and it now works out 0.5855. Cool. So that's my critical region. So critical is when the mean is greater than 0.5855 or less than or equal to 0.5745. Anything outside of those values would be critical. All right, so if we now look back at the part B of the question, the mean is calculated to be 0.587. Cool. Okay, comment on this observation in light of the critical region. So 0.587. Okay, where does that lie? Well, our critical value here was 5745, so it's not critical on this side. On this side, 585. So 587 is more than this, so it's going to be up here, which is critical. So that is more than 0.5855. Therefore, critical. So we can do all the things. So we're going to reject H0, except H1. Sound the alarm at the factory. The bolts are coming out wrong. So there is evidence to suggest, what were we testing again? The mean diameter has changed. The diameter has changed. Cool. Okay, have a think about that. Ask me if you've got any questions. That's how I always want you guys to do these. So sketch it, find the critical regions, compare their value to your critical values. What does x in from the calculator actually represent on the x-axis? It just means the x value. So yeah, it represents these numbers. So this is the bolt diameter. This is the mean bolt diameter. This is the critical bolt diameter. It's any bigger than this, and we're saying we've got a problem. Any bigger than this, and it looks like statistically our bolt diameter has changed. It's no longer, our bolts are no longer coming out the machine with an average of 0.58, which is what they should be. They should all be
all our bolts should be around this average. If they're coming out over here, it's so much so the average has probably changed from 0.58 and our bolt diameters are no longer correct for our machine. So any machine producing anything, there's a margin of error and there's an acceptable margin of error as long as the average is still statistically 0.58. This is so unlikely to happen if this is the average that we can accept, we can kind of guess that the average has changed. So if this is the value we've got, the average has probably increased a bit. So something's wrong with our machine. We need to fix it. Does that make sense to everybody? So we're finding which values would be so extreme they are likely to come from a different normal distribution, a distribution where the means have increased or decreased in that case. Good. Okay, I'm going to try some more. Literally, this is all we're doing today, is practicing these. And we're doing very well for time, so hopefully I'm not going too quickly. If I am, just pause, rewind, and you'll be a bit out of sync, but that's okay. So, next question. Let's just move this down. Okay, so the mass of European water voles is normally distributed with standard deviation 12. Given 2.5% of water voles have a mass greater than 160, find the mean mass of a water vole. Then we told 8 water voles chosen at random, find the probability at least 4 have a mass greater than 150. And then we got a hypothesis test. So I would like you guys to try this one. There's a lot going on in this though, so I'm going to give you some hints. Part A is just a kind of standard normal distribution. You're trying to find a mean. So this is what we did last Friday. I think we did this last Friday. So we're trying to find the mean using, remember, Z normal with 0 and 1. Yeah, so that's part A. Part B is a binomial distribution question, which is nicely disguised. So I think we're going to have to do a bit of a normal distribution followed by binomial. So this is normal, then binomial, which I think we did one of these on Monday, possibly Friday as well. And part C is a normal hypothesis test. And it says it's different, so I'm just going to leave that highlighted. Okay, so this is 10 marks worth of questions. I'm going to be nice and give you guys 12 minutes because I think we are a bit ahead today. And I would like you all to have a decent stab at this. So I'll set the timer for 12 minutes. Comment your answers when you get them, and I'll tell you if you're correct or not. And if you need any hints, let me know as well, and we'll go through this in 12 minutes time. Cool, give it a go. Cool. All right. Let's call it. Okay. Yeah, some good answers in the chat there. Let's go through this. So, there's not gonna be room to do it all on. Maybe there will. We'll see if we can fit it all on one side. So, find the mean mass of European water vole. Okay. So we know M, normally distributed. We don't know what the mean is, that's what we want to find. Standard deviation is 12 squared. And we're told that M greater than 160 is 2.5. So the way we do this is with the Z equals X minus mu over sigma. And the reason we use this is because the calculator needs you to input mu and sigma to find stuff. So we don't know mu, so we can't use the calculator for that distribution, but we can use the calculator for a Z distribution because you know Z is a normal with a mean of 0, standard deviation of 1. So we can do the question with this. Find Z, put Z in, put X in, put sigma in, and then code it, uncode it to find out what mu is. So if we do a quick sketch, just so we know what our distribution looks like. Probability it's greater than this is 2.5%, so that's going to be our Z value there. And that's going to be 0.025. Let's bring up the calculator for an inverse normal, which we're already on, which is useful. So tail is going to be to the right. Yep. Area is going to be 0.025. Sigma is going to be 1. Mu is going to be 0. And that gives us a value of 1.96. Z is 1.96. So we're now going to code that back into an X value. So Z 1.96, so 1.96 equals X. X was 160 minus mu, we don't know, over sigma, which was 12. So if we uncode that on the calculator, 1.96 times by 12 and do 160 minus that answer, we get mu as 136.48. So yeah, we'll call it 0.5. Cool. Right, so we can now write that up in our mu up here. So 136.5 and 12 squared. Cool. All right, let's do part B. I need to clear the screen. All right, so part B. 8 voles are chosen at random. So we're looking at binomial. So X, B, number of voles, 8. Okay, now we want the probability that they have a mass greater than 150 grams. We don't know that. So I'm going to put P there, and this is the probability that M is greater than 150. We want to find the probability X is at least 4, greater than or equal to 4. So this is binomial. But to do this, we need to find this probability, and the way we're going to find this probability is with a normal. So we need to find the probability that the mass is greater than 150. We know all of our stuff, we just worked it out, so we just worked out the mean. We know sigma, we can find this relatively easily. So we're going to find this, put it in here, do this, and then that's our answer to part B. So if we bring back the calculator, it's not inverse this time, it's a standard or a normal distribution. So go to normal, NCD, lower is going to be 150, upper is something big, sigma is 12, and mu is 136.5. So type it all in, do a nice little sketch if you've got the option. execute to me, and we get the probability is 0.1302. Cool. Okay, let's put that back in. So this is going to be our probability over here for our binomial. So if we go out of this into a binomial distribution, to dist binomial. So we know everything, we just want to do greater than, so it's going to be a cumulative with our lower as 4 and our upper as 8. If you've got class viz, I think you're going to have to do the whole 1 minus thing for this, so be careful if you're doing this on a class viz. Number of trials is 8, and probability of success is 0.1302. Boom. Equals. Go. Do it. Solve. 0.13 is our probability. So, yeah, weirdly, it's similar to that's for the probability there. We get probability 0.1302. Some of you got 0.1, which I did when I did this yesterday. That's if you don't round the mean. So if you kept it as 136.48, you get 1 point. Have I left out a 0? Yeah, 0.013. If you got 0.0129, yeah, it rounds to the same thing to 3 decimal places. That's good. Okay, the last part then is asking us to do, we've got a separate sample, so we've got a separate thing now, so let's get rid of everything so far. We're now looking at different species of creature. We're looking at water rats instead of water voles. So, blah, blah, blah. So normal distribution, n grams, so the weight of these rat things is a normal with a standard deviation of 85. And the mean, if we keep reading, we want to test if it's different from 860, which is what it says here. So our mean is going to be 860. Our mean distribution will be n, 860 still, and we're going to have 85 squared over the sample. The sample is 15. So we're all, let's get rid of the calculator for a sec. So all set up, ready to go. All right, we need to state our hypotheses. So H0 mu is 860. H1, it's a two-tailed test because it says different. So mu is not 860. So trying to find the critical regions. 10% significance, we got 0.05 and 0.05. So find these critical regions, use the calculator, find what they are, and then test if what was our test statistic? 875. We're going to test if that is any different. So bring up the calculator. We're doing inverse normal this time. So distribution, normal, invenim. Cool. Okay, we'll do the left tail first, because that's what people with the class wizards can do naturally. Area 0.05. Sigma is going to be 85 over square root of 15. And mu is 860. Cool. All right, down we go. Execute. So our lower critical value is 823.9. And the upper one, we'll just go back. We're going to change the tail to right. And be 896.1. Yes. Cool. Okay, well, what's our test statistic? So the test statistic we've got is 875. So 875, somewhere in there. So it's not going to be critical. So 875 is less than 96.1, therefore not critical. So therefore accept H0. and say maybe there's no reason to suggest the mean is other than 860. So suggests mean is 860. Cool. All right. How long we got? Half hour left. We're doing really well today. Okay, I want you guys to try another one on your own. So we're going to try one from the large data set. As if anyone's got any questions, now's the time to ask before I throw you in to do another one on your own. No? Okay. So we're going to try this one. It's pretty standard question really, this one. Go back to the calculator. Let's move it down a tad. There we go. So daily mean wind speed distributed with tons of it's a pretty straightforward question. It's only asking about the hypothesis test part. So 4 marks. Let's make it strict. Give you 4 minutes. See how you get on. No, Dan, you're still there. I can still see you. Um, okay. So Dan's got his. I see what you've done now. You've said yes. The mean is greater. All right. Let's have a look at this. Oh, I need to turn the camera on. Control M. Cool. All right. So we've told. Blah, 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 blah. So yeah, let's write our distributions down. So we get W is normal with mean of 9.5. Sometimes you've got to read through to find the population mean. So we're trying to prove it's greater than this. So that's what our population mean is assumed to be. Standard deviation 3.1. Okay, so our sample means is going to have a distribution of 9.5 and 3.1 squared over 25. State your hypothesis clearly. So H0 mu is 9.5. H1 mu is greater than 9.5. You guys can see that, can't you? Let's shrink. Cool. So test at 2.5% level. So we're looking for this bit 0.025. Trying to find this value, see what it is. It's not 0, it's not like that. So if we bring the calculator up, and go to Invner, tail to the right, yes, area 0.025, sigma 3.1 over square root 25, 5, did it in my head like a pro, and mu is 9.5, cool, down, come on, go down, execute, and I get 10.7, 10.71, well, it's 10.72, cool, hide L calculator. Okay, so given the mean of the sample is 12.2, that looks bigger. Dan said the mean is great. Oh, cool. Is that what I got as well? I did do this yesterday. Yes, the mean is greater than 9.5, so 10.72 is greater than 9.5. Therefore, reject H0, accept H1, the mean wind speed is greater. Cool. All right. Everyone okay with this? Once you got this, it's easy stuff. Don't we need to say it's greater than it? 12.2. Did you get 12.2? Wait a minute. I'm being an idiot here, aren't I? What have I done? Yeah, I've written something stupid here. Given the mean of the sample is 12.2. Yes, I've done this weirdly. Sorry. Yeah, what am I talking about? Came to the right conclusion, but for wrong reasoning. 12.2 is our test statistic. 12.2 is greater than. Of course, 10.72 is greater. That was really stupid what I just said. Yeah. Sorry, guys. All I said was the critical region is more than the mean. Well, always it's going to be more than the mean in this case. Yeah, we need to use this test statistic. 12.2, thank you, guys, is in the critical region. Therefore, we reject him. I wrote the wrong thing there. Cool. Everyone's okay. You've all exploded in the comment section, as is customary on YouTube, but you were right. So, well done. Yeah. Cool. Everyone okay now? So, put your critical value. Test statistic against your critical region. I used the mean, which was stupid. Cool. Anyway, let's move on. So we've got bags of time. I've got two more questions to try. I think we'll do the climbing rope question because that one's quite interesting. And I quite like climbing. So we're going to try this one. Yes, good. It all fits on the screen. So climbing rope. Blah, blah. I'll give you some hints because we are still quite fresh at this. So part one is a normal question. Nothing weird going on here at all. So that's me NCD. Part B. B gets a bit more interesting. It's a normal question, but using the sample means. So you'd think, sample means hypothesis test. No, it's just a normal question, but using the the mean distribution instead of the ordinary normal distribution. So it's a bit weird, but nothing too difficult there. But make sure you use the right distribution because we're talking about means. And then part C is a normal hypothesis test. All right, so this is 8 marks worth. I will give you guys 8 minutes to do it. Yep, and we'll come back in 8 minutes. See you on. Feel free to comment your answers, and I will see how you get on. So back to the timer. 8 minutes. Go, go, go. Yeah, 0.0342 is what I would have gone for myself. Good, good, good. Part B, Sam, is find your mean distribution. So remember, take your sigma and divide it by n, or root n in this case, and then just do normal distribution, but with the mean distribution instead of the standard one. All right, let's have a look then. So, still not sure what mean to use for B. That should be the same. The mean should be the same for part B. All right, let's go through this then. We might have time to do one more, which would be good. Okay. So for part A then, let's write our distribution. So we know the mean is 170.2. So climbing rope, I'm going to use B for braking strength, 170.2, and then we got 10.5 squared. Okay, so we want to find that it's 175 to the nearest kilogram. So what that means really is we're looking for the probability it goes from 174.5 to x to 175.5. So that needs to be your workings. If I bring up the calculator, we're looking for a NCD normal distribution, norm, NCD, variable, lower, 174.5, upper, 175.5, sigma, 10.5, and mu, 170.2. Cool, execute. We'll draw it as well, always. So it's that little bit there. And we get 0.0342, as you guys all suggested. Decent. Okay, part B. So part B is now telling us random sample of 50 is taken. So we're trying to find the probability that the mean braking strength is greater than 172.4. And we know the mean distribution is same mean, 170.2, and sigmas can be 10.5 squared over how many other? 50. So it's the same thing really, but using the mean distribution instead of the basic one. I always have to be careful saying the normal distribution or the standard because standard means something as well. So lower is going to be 172.4. Upper, I'm just going to stick in 1000 for that one. Sigma 10.5 divided by square root of 50. And mu is the same. So you should get 0.0692. Of course, everyone wrote that. I know a few of you were saying you weren't sure what it meant. It is worded weirdly worded. So find the probability that a random sample of 50-meter lengths will have a mean breaking strength. So that's how I knew. Second, you see the word mean, we're not looking at the standard distribution, we're looking at the mean distribution. Cool. Right, so then we've got the hypothesis test part. So I'm going to move the question up to get a bit more room here. Cool, so they're adding something new to this rope. And the manufacturer believes that it's going to increase the... Oh, let's get rid of the calculator for now. So new things added to the rope. Manufacturer believes it will increase the mean breaking strength without changing the standard deviation. Okay. So sample of 50 lengths is found to have mean breaking strength for that. Okay, so we're doing hypothesis test. Our mean distribution is the same as I wrote just now, 170.2, 10.5 squared over 50. Make some space. So we're trying to test if what they're doing to the rope is going to make it better. So increased. So it's a one-tail test. We've got H0 mean is 170.2. H1 mean is, we want to increase, so greater 170.2. Sketch it. We're testing at the 5% level, so there's 5%. We want to try and find out what the critical value is, and then we want to test if our test statistic of 172.4 is greater than that critical value. So back to the calculator. Inverse normal, tail to the right, distribution, norm, invner, tail to the right, area 5%, so 0.05. Okay, our sigma is going to be 10.5 divided by square root of 50. I've put an x there, 10.5 divided by square root of 50. And our mean is still the same, 170.2. So if we work out this one, we get the critical value, 172.6. Okay, so we're trying to test if our mean breaking strength of 172 is critical. So I get rid of the calculator. So is it critical? Well, it's not. 172.4 is just inside, so it's not critical. Therefore, not critical. We should probably say as well, critical would be greater than that. So because this is less than, it ain't critical. Therefore, reason to suggest rope hasn't improved. Sad times for the rope manufacturers. But, I mean, that was 5% level, and we're very close. We were in 0.2 of it. So maybe if they tested at the 10% level, maybe that would make all the difference. Maybe then they could say, yeah, our rope's better. But they'd have, more error. So we had 5% error in our statement. If they did it for 10%, they'd probably get it. But they might have a 10% error in their reasoning. Cool. Right, we've got 8 minutes left. I'm not going to try the last question because I think we're out of time. I'm instead going to show you guys on Moodle how I want assignments to be done from now on. So the first assignment's going to be due tomorrow, but it's actually the assignment that was due last Friday when I wasn't in. So, as long as no one's got any questions about these distributions, we'll probably do a couple more of these as a starter in tomorrow's lesson. Okay, here we go. So got the internet up here. The internet. We're going to go on to Moodle. Log yourself in. Go to maths, so my courses. Maths. Ah, I can't see if there's any comments anymore. I just closed the stream. I hope that didn't actually close the stream. Give me a sec just while I. Oh, I hope it didn't close the stream. Go live. If you can all see this, this is interesting. This is how you do YouTube. Um, Come on, don't say I closed it. Still there. Let's click that. Are you still here? You guys still here? Yeah, you guys are still here. Yeah, I've got 7 8 which got bookmark. So I can check my page. I got my COVID dashboard. Yeah, all the stuff you need. Insight into my life. All right. Anyway, so we are here on our Moodle. If you scroll all the way down to the bottom, and we've got skills checks and assignments. So basically, from now on, I want you guys to do your assignments like this. So assignment 24 is the one that was due last Friday. So you should all have done it. I'm going to assume you've all done it. Progress check, if you guys could do tomorrow or just some point soon. There's a skills check. There's some instructions here, so it says upload your assignment. I don't mean upload the whole thing. All I want you to do is upload any questions you've struggled with. If you didn't struggle with anything, just a photo of a thumbs up or something to show you've done it at least. And then I want you to upload the full workings for the skills check. So upload as many files as you need. Uploader is here, so click on that, upload your files. Or I think you can drag and drop them. So just drag and drop your photos there of the assignment and of the skills check. You need to upload 2 files, so I do want to see the skills check and the assignment. Then you type your answers here, so you can see the question has asked you for the tension and the resultant force. Type the tension in there, so let's type in 23. Type in resultant force 1. I'm going to get it wrong. Then if you click next, submit all and finish, and we get told off because I didn't upload anything. So I got this one hasn't been marked yet, but if you look, I haven't actually uploaded anything. So it says I need to upload 2 files minimum. So please upload your files there. It will give you the correct answers, so you get a rough idea if you've done it. And if you want to do it, you can go back and try it again. So if I want to try that quiz again, I can go back to Moodle, back to that quiz, and go in and try again. And then I'm going to mark these every week. So I'll have a look through all your workings. I'll look at your answers. If you typed it in badly and you think you should have got it right, I will see that, correct it, and give you the right marks. And then I can see your grades. And that's how we're going to do assignments from now on. So if you got any questions about that, what does it say here? I think you have, yeah, if you guys handed them in, they're at college, so I'm not going to be able to get around that. So for 24, 25, I think I've ticked them off already. I think I did all my marking before I left, so I will tick those off online anyway. Not every page. Unless you struggled with every page, then do it. But if you just, just either a photo of the front page saying I did it with a thumbs up, or a photo of what specific questions you need help on. How many more weeks of stats do we have left? For the syllabus, 1. So 1, yeah. Maybe 2 lectures after tomorrow. So 3 lectures left in total. So we will be done very soon after Easter. But obviously because we're a bit behind with the assignments, you can see where's it gone? There's quite a few assignments to do because that one. But if you can work through these at your own pace. They're all there. All the skills checks have been uploaded. All the answers are there as well. So yeah, this one's a bit rubbish because you have to write it all in words, and obviously the answers are going to come out slightly different to what you've written word for word. But I can check through. You get a rough idea of what you needed. But yeah, everything's there, so that's the main point. If you wanted to do all of it next week, you could finish all the skills checks, all the assignments, and be done. But yeah, I would like you guys to work through these when you can. If you want to do one a week, you can. If not, don't. What we're going to do after, we're going to be revising, possibly not for anything, but we need to make sure you guys know your stuff, regardless of what's going to happen. So yeah, we'll be revising after that. I think we'll go through pure because I've done stats as we've been going, and I've also got the first year videos for stats, so you'll be able to look at stats again if you want to on your own. And I'll have done mechanics videos for further maths, so you'll be able to revise further maths as well. So if you want to do any more revision on stats or mechanics, look at my other videos that I'm uploading. It's all stuff that's relevant to you guys, and I've done it in mind of you guys being able to revise. So when I've been teaching mechanics to my further maths kids, I've made sure to go right from the start all the way through, like it's a really good revision. Tutor, I don't really know what's going to happen with Tutor. We've not been told. Basically, my plan for today is just to drop you guys a message and we can do video chat if you guys need help with anything. And we can use it for like workshop session. But at the moment, not sure what's going on with Tutor. We'll be told at some point, but you will need to swipe for it. So I'll need some way of checking attendance, even if it's just a message on Teams. So I'll message you guys on Teams through the Tutor channel, and you know that's how we'll do attendance for Tutor. Anyone else got any other questions? I think that's bringing us up to the end for today. So there's one more lecture tomorrow on normal distribution, which is just kind of rounding everything off, and then we're moving on to our last topic after Easter holidays. Cool. I'll wait a minute just to see if anyone's got any questions. I will be doing workshops, so if you want any help with stuff, with questions, email me them in the week, and I will do a workshop session um, every Wednesday, 10 past 1, and I'll just do the questions that you were stuck on. So email those to me if you need any help. Anyone else logged in that didn't give me the register earlier? I'm still missing a couple of you guys because attendance does still matter. I've got Isaac, Sam, Carrie, Zach, Lottie. If you guys are there, please let me know. Or if you watch this in retrospect, please email me so I can tick off that you have watched this lecture. All right, cheers, guys. I will speak to you tomorrow in the morning. See you then. Bye.